Hey guys, so this will be a quick crash course on magnetically coupled coils. So let's start first with Faraday's law. So Faraday's law states that a voltage is induced by a time-varying magnetic field. So if I were to take an inductor or a coil, and if I were to take a magnet, let's say, and sort of move it inside this coil, it would induce a voltage at the other end. Similarly, if we have a voltage applied and you have a current flowing, we know from physics that, from right-hand rule, that there's going to be a magnetic field that's produced by the current inside. So it goes both ways. Now, let's discuss what all these things mean. So phi is the flux, the magnetic flux, so the flux of the magnetic field. This can also be written as n d phi di, where I is the current in your inductor, di dt. This is sort of like doing a chain rule. So this part is called L, it's your inductance. And from here we get our familiar equation, which is V equals L di dt for the inductor. So let's say we were to have two inductors next to each other. And let's say one of them was powered by a current source, and the other one is left open. So the current in here is I1. The source is I1. The voltage across this inductor would be V1. And we're going to call this voltage at the other end, the open voltage, we're going to call it V2. This inductor has N2 coils, this one has N1 coils. This has inductance L1, this has inductance L2. So as the current flows in this inductor, it's going to create a magnetic field. Something like this. It's going to flow like this. Now, the magnetic flux that does not reach here, right? There's going to be some magnetic flux that goes like this and falls here. It doesn't go and reach here. There's also going to be some magnetic flux that is going to go here and reach here. And because we're dealing with an AC signal, right, it's going to create an AC magnetic flux, a changing magnetic flux, and that's going to create a voltage, an AC voltage at this end. So the flux that reaches this coil will actually induce a voltage here. The flux that does not reach this coil will not influence this voltage here. So the flux that doesn't reach this coil, we call that, so the total flux produced by this whole current going through the coil is phi1. The flux that does not reach this coil is called phi11. The flux that does reach this coil would be called phi12. So the flux from coil 1 that reaches 2. This is the flux from coil 1 that goes into itself. So the sum of these two is the total flux produced by this coil. So let's say we wanted to write the voltage. V1 of T is going to be, using Faraday's law, N1 d phi1 dt. Again, we have, now phi1, to recall, is the total flux. So that's, this voltage here is going to be, by Faraday's law, N d phi dt. That's the voltage here. And this is the total flux. So this is going to be N d phi1 di1 dt, using the chain rule. Now this is going to become L, we'll call L1, and this is di1 dt. Now, let's say we wanted to find the voltage at this end. So V2 is going to be, well, we have N2 turns. Now, what's the flux? The flux is going to be phi12, the flux from this side. There's nothing connected here. So the only, if we're going to get a voltage here, it has to be from the changing magnetic flux that comes from this end. So from this coil that reaches coil 2. So it's phi12. This is going to be N2 d phi 1, 2. Well, what's causing d phi 1, 2? That's I1. So it's di1 dt. This is called M21. So it's the mutual inductance. So it's called M21 di1 dt. So M stands for mutual inductance. It's the mutual inductance on 2 caused by 1. So that's why it's 2-1. Okay. So now let's say we do the opposite. We keep this coil 1 open, and the other side we connect it to a current source. This is I2. This is N2, N1. This is plus minus V1. This is plus minus V2. So, again, we're going to have some magnetic flux that doesn't reach coil 1. It's going to go like this. This is phi2, so the total flux caused by this coil is this phi2 plus the flux that actually reaches coil 1 from coil 2, like this flux. This will be called phi21. So the total flux produced by this coil is going to be phi22, which is the magnetic flux that doesn't reach this coil, plus the magnetic flux that does reach this coil, which is phi21. So let's say we were to look at V2. That's going to be N2 d phi2, right? Because we're on this side, so that's the total flux. The voltage here is the number of turns times the change of the total flux here with time. So that's going to be N2 d phi2 di2 dt, because I2 is causing this. And this part is going to be called L2 di2 dt. Now let's look what happens on the other side. You're going to have N1, because we're on this coil. What's the changing flux? The changing flux can only come from here. So the whatever flux reaches this, that's phi21 dt. Again, N1 d phi21. What's causing d phi21? I2. So it's d phi21 di2 dt, where this part is called your M12, mutual inductance. M12 di2 dt. There was the mutual inductance on 1 caused by coil 2. So if we were to use conservation of energy, we can show that M21 equals M12, and we can call that M. There's only one mutual inductance. So the definition of mutual inductance is the ability of one inductor to induce a voltage across a neighboring inductor. And now this mutual inductance is measured in henries. So when we have conductors in close proximity to each other, we often use what's called the dot notation to show how they are mutually connected. So let's say the dots are like this, and let's say you have a current coming in here. When the current comes in, right, comes in with a plus, leaves with a minus. So if there's a plus on the dot, then on the other dot you're also going to have a plus. Let's say, again, you have two inductors, dots are on the same spot. But let's say now the current is coming out of this dot. So it's as if the current were going in here, goes in here plus this minus. So the minus is going to go transfer to the other side where the dot is. Now sometimes you're going to see, let's say you have a dot here and a dot here. Again, current coming in here, well, plus minus. Well, the plus is going to match with the dot on the other side, like this. Similarly, if we have same thing like this, you have a dot here, and then you have a dot here. If the current is coming out, it's like the current is going in here, so it comes in plus, out minus. The minus is on the dot, minus also goes on the dot here. And that's how you would find the voltage on the other side. So let's say we have inductors connected in series. So let's say we have a series aiding inductor. It would look something like this. You have a dot here, you have a dot here, current is coming in. This is L1, this is L2, this is plus minus V1 of t, this is plus minus V2 of t. And then the total voltage across would be V of t. So, V1 of t, well, it's going to be, oh, by the way, this current is called I1. V1 of t is going to be L1 di1 dt, so that's the inductance from the inductor due to itself, so the self-inductance. But notice this current is also running through here, the second inductor. So when the current runs through here, comes into the dot plus, minus. So what's going to happen is it's going to induce here a voltage, right? It comes into the plus where the dot is, leaves out the minus. So the dot, it comes in with into the dot with a plus, so it's going to induce here plus, minus. So it's going to, you're going to have here a mutual inductance di dt, where this I is the same current that goes through here as here because they're connected in series. So for voltage, the voltage across this inductor is, you have an inductance from itself, but you also have voltage produced by this guy, by mutual inductance, that you have to consider. Let's look at voltage V2. Well, you have your self-inductance, which is going to be L2 di1 dt, right? But this current is also flowing through this inductor. It goes in plus, out minus. So in plus for the dot is going to transfer here a plus, minus. So it's going to be plus M. This, I forgot to put a 1 here. It should be plus M di1 dt. So the voltage across this inductor is the self-inductance, so the inductance due to itself, and also there's going to be a voltage induced here from this guy because of mutual inductance. So if we were to add these together to find the total voltage, V1 of t plus V2 of t, well, we would get V1, which is L1 di1 dt plus M di1 dt plus L2 di1 dt plus M di dt. Well, di1 dt. This I is the same for all of them, so I can take di1 dt out as a common factor. I'm left with L1 plus M plus L2 plus M, and our common factor is di1 dt. So I can combine inside, I get L1 plus L2 plus 2M di1 dt. And this is your voltage, your total voltage. Now, this is called your series aiding inductance. And it's the sum of these two inductances plus twice the mutual inductance between the two. So now, what about a series opposing inductance? Series opposing. So again, you have two inductors connected in series, but this time the dots are not in the same spot. So here you have your current coming in, I. This is L1, this is L2, plus minus V1 plus minus V2. And your total voltage is going to be plus minus V. V1 of t is the voltage across this inductor. So that's, you're going to have self-inductance, which is L1 di dt. But this same current is running through here. So it goes, where is my, right here? It goes in plus like this, minus at the dot. So there's going to be a minus transferred here. So notice the mutual inductance from here is opposite the self-inductance here. So you would have to write minus M di dt. So again, the voltage across this inductor is caused by, first, its self-inductance and then the mutual inductance here. But because the current is coming in here and coming out of the dot, the mutual inductance is opposing here. So you have a minus. So V2 similarly, well, you have your self-inductance, which is L2 di dt. But then, remember, the current that flows through here was also flowing through here, right? So it's going to go into the dot here, so in plus, out minus. So there's going to be a plus induced on this dot. But notice, it's opposite of the original sign. So the mutual inductance here is opposing the self-inductance here. So again, you have minus M di dt. If we were to add these together, you would get V equals V1 plus V2, which is going to be L1 di dt minus M di dt plus L2 di dt minus M di dt. So di dt is a common factor because it's the same current. So we're going to get L1 plus L2 minus 2M di dt, and this is going to equal V. This is called your series opposing inductance. So let's look at a quick example. Mutual inductance is an inductance that happens between two inductors. So when you're analyzing a circuit and you're in the frequency domain, you need to consider the impedance that's caused by a mutual inductance. So let's look at an example. Here you have voltage source, resistor, inductor. Here you have inductor. Same thing, mirror image. So this is V2, this is R2, this is R1, this is V1. This current is I1. The impedance of this inductor is J omega L1. Impedance of this inductor is J omega L2. Now, there is a mutual inductance, and that impedance would be J omega M. This is current I2, and the dots are as such. So let's say we wanted to analyze this circuit. So we're going to use phasors. We're going to write KVL first in this loop. So it's going to be 0. I'm going to start here. 0 equals minus V1 phasor plus I1 phasor R1 plus J omega L1 I1. Now remember, there's also current flowing in here. So the inductance here is not only due to itself, but also due to the mutual inductance caused by this current creating a magnetic field here that's going in here. So there's a mutual inductance from this side that's affecting here. So not only do we have J omega L1 I1 just from this guy by itself, but also there's something from here that's affecting this. So it's going to be your mutual J omega M. But what current is causing this? It can't be this current, because then it would just be self-inductance, right? Mutual inductance is caused by another inductor. So this is from I2. We move V1 to the other side, and we're left with, combining the like terms, we get R1 plus J omega L1 I1 plus, and here we have J omega M I2. Let's write KVL for the other side. So let's say I start here. 0 equals minus V2 plus I2 R2. Then we get here this inductance, which is gonna impedance is gonna be J omega L2 I2. But remember, we have current here, which is going to cause a magnetic field in here, which is going to influence this. So we have not only self-inductance from this guy, but we have mutual inductance from here. So we have to add J omega M. But this mutual inductance is not caused by I2, because if it were caused by I2, then it wouldn't be mutual, it would be self-inductance, because it's caused by itself. Mutual inductance from this side. So it's going to be J omega M times I1, because I1 is causing this mutual inductance. So again, we have here, we bring V2 to the other side, we combine like terms, and we get R2 plus J omega L2. This should be I2. Plus, and then we have J omega M I1. This would be how you would analyze a circuit with two inductors that are coupled. So before we close, I want to mention one last thing, which is the coupling coefficient K, which is equal to mutual inductance over the square root of L1, L2, the inductance of each coil. So, coupling coefficient. This is the coupling coefficient. So, before we get to the coupling coefficient, I just wanted to say, how did we know this was plus? I sort of rushed through it. So let's quickly just go back here real quick. So let's take a look at KVL here, right? So again, we have the inductance of this coil by itself, but then you have mutual inductance here. So, how do we know it was plus? Well, this current is flowing this way, right? So current goes into the plus, out the minus. So the plus on this dot is going to transfer here like this. So, and the current is flowing like this. So the current sees a plus. So it's going to be plus J omega M I2. If the dot were over here, it would be reversed and you would have a minus. But in this case, it's a plus. So, and we were going in clockwise direction here, so if we see a plus, then we put plus here. Same thing here. When the current goes in here, you have, it goes in plus, out minus, then it appears here on this side, plus, minus. So the mutual inductance, again, current is going this way, so we see plus first, then minus. That's why I knew to put a plus here. If this dot were over here, it would be a minus, but in this case, because the dots are in the same spot, it's plus. That's how I knew it was minus. So don't forget that when you're analyzing your own circuits. So back to coupling coefficient. Coupling coefficient is essentially a measure of how much one coil affects the other. It gives you a measure of how strong the coupling between the two coils is. In a way, it's basically a measure of the magnetic coupling. So K is a number that ranges between 0 and 1, where 0 is no coupling at all, and 1 would be perfect coupling. They're sharing flux equally. So that concludes the crash course on magnetically coupled coils.